Welcome to the CFA Colloquium. It's my pleasure to introduce today Raffaella Margutti, who's a longtime collaborator and a great colleague. And many of you know her from her time here. Raffaella got her PhD from University of Milano and then was a postdoc for a couple of years at Brera Observatory in Italy before coming here to the CFA in 2011. And she was here with us for 4 years doing a lot of great work on various types of transients and perfecting the art of what she liked to call science with zero photons. And that's great for X-ray astronomers. And then she moved to NYU for a year and from there to Northwestern University in 2016 as an assistant professor, where she's now doing really exciting work. Today, I think she's going to tell us about several very exciting events ranging from gravitational waves. And for those of you who've been following the news, maybe she'll tell us about the cow, and you'll find what that is. But in any case, she's going to tell us about discovery frontiers in the new era of time-domain multi-messenger astrophysics, which has all the great buzzwords of our current age. So take it away, Raffaella.
Yes, thank you for the introduction. It's very exciting to be here, and I feel like the same sort of pressure that you have when you report back to your parents or what you have been up to. So with this kind of feeling, let me get started. So I want to share with you a few things that are new in our field of time domain astronomy, and hopefully give you a little bit of a feeling of where the frontier is, where is the place where our knowledge ends and where ignorance starts. So I will start with a little bit of context, very short. That is always important, and so why I studied transients in the first place. So there are many reasons, so I'll go very quickly here, but we all know that some transients, type 1a supernovae, are very important for cosmology. But if you don't care about cosmology and you care instead about chemical evolution of the universe, well, massive stars, when they explode, they give back whatever they synthesize in their interiors. So that's the way, one of the ways the universe enriches in chemicals. While doing that, they also transfer kinetic energy, and this is how supernovae participate in galaxy evolution, as we started to appreciate more often recently. And of course, supernovae, stellar explosions, is the way we create this compact object, neutron star, black holes, and I'm sure that here you might have heard that sometimes emerge, and they give us some extra work to do while we look for their counterparts in the electromagnetic spectrum. Okay, so here is the basic picture of a star, and this star explodes. So what are the big questions in our field right now? There are two main components that I'm really interested into. And the first is very simple. So when we see a star that explodes to us, it looks very often like this. What this means, basically, we see radiation from the exterior, but we have no clue what's going on inside. So the first question that we are trying to understand, and I'm trying to understand with my team, is how we get there. So which kind of star produce what, and how that star gets to the explosion. And the second part of the story, where we still have a big question mark, is what this explosion produced. Do they produce a black hole? Do they produce a neutron star? And here I put 87A, just a great example of a very nearby case where we still have no clear detection of either. So the way I try to answer to these big questions is just allowing every photon to count. So putting together things from the gamma rays all the way to the radio. So it's an inclusive approach. That's the way I like to define it. But we also try to be inclusive in terms of perspectives. So we study with this great team of young minds both what happens before the explosion, what happens during the explosion, and what happens after that. So we try to cover it all and try to attack the same problem from multiple perspectives to find the answer. So that's the strategy. So why now is a good time to approach these questions? We have been having these questions since quite a while. And again, I'll give you 2 points. And the first is very much related to a technological revolution that is the thing that is allowing us to literally monitor the sky, the night sky, in real time. So we can see new things every night. And here I put some major key players, and I put also LSST because this thing is eating up a lot of my time right now as I'm helping designing the gravitational wave strategy of all apparatus T. But the important thing here is that this kind of revolution is not going to be limited to the optical. It will be happening in the radio, and hopefully, I really, really hope that the X-ray part of the spectrum will also get there with wide field instruments. So what have we been doing with these great tools? So first of all, we could explore new regions of the parameter space of things that we already know. So supernovae, in the supernova world, until let's say 10 years ago, we were relying on amateur astronomers, which are great, amazing people, but they're people. So they tend to see things when they're bright, right? Yeah. So which means that effectively we were starting sampling the supernova explosions from here and all the way down. So we were missing out on whatever happened in the early phases, which is actually very important, and I will call it rise time science, and also pre-supernova outbursts. So right now, it's kind of accepted that yes, supernovae, the stellar progenitors, they do experience outbursts before death, before the big explosion. But back a few years ago, that was not an expectation. So that was one of the things that we found. So what else? We were also able to find some new types of transients. And this morning, I told you something about superluminous supernovae. And today, I'm going to concentrate more on this other type of transients, which I call fast-evolving transients. So let me give you a hyper-simplified explanation of why these things are now things that we can find, and before we were not discovering them. So here I put a cartoon of a very fast-rising transient and a superluminous supernova-like, so something that takes time to get to peak. And before, what we were doing is basically something like this. So we were sampling transients, let's say, with this cadence, which means effectively we were blind to very fast transients, and we would never trigger on this superluminous supernova just because the delta brightness was not enough to trigger. So right now, what the new surveys are doing can be visualized like this. So way denser sampling, and let's stare at the same patch of the sky over and over again, season after season. So you do realize right away that now this kind of transients can't hide anymore. We can see them. So that's why, by sampling different time scales, we are now in the position to discover actually these fast transients and superluminous supernovae. The other piece of the story of why we are now in the position to find new stuff is because we are allowing every galaxy to shine in our sample. So we're not staring at just the beautiful galaxies, but we're allowing every galaxy to produce a transient that we can discover. So these untargeted searches are finding a number of transients in galaxies that are not the ones that amateurs would stare at. And these are actually incredible factories when it comes to weird transients. So these two pieces, timescales and untargeted surges, is what, at the end of the day, are allowing us to discover new things. The other point that I want to make about why is now a good time to try to answer these questions is very much related to the fact that we can do a good job across the spectrum. So if you want to constrain the physics, the point that is very close to my heart is that if you want to constrain the physics, you need to use every photon that the universe gives you, gamma rays to the radio. And this is just a first step towards what is actually right now reality, multi-messenger astrophysics with gravitational waves and neutrinos. So let's get started. Let's dive in a little bit more. So I will start with the first part of the problem. So how I am trying to make progress in understanding which stars explode like what, and what do these stars do just before stellar death. So how do we sample these last 1,000 years of life? This is a big question mark in stellar evolution, and this is also the place where theory stops to be very predictive. So observations needs to provide guidance here. So here are 3 ways we are using to study this this phase of stellar evolution, and the first is direct observations. This is as easy as it sounds, as simple as it sounds. By staring at the night sky every night, we can see what the stars are doing. So we can find these outbursts just before the main explosions. since our surveys are good, have been good in the last years, we are building up a good knowledge of what stars have been doing in the last years or so of life. Another, and this is the way that back a few years ago, we were able to find outbursts before the main explosion of the supernova. What I find very intriguing is that now we know that this kind of outbursts are actually common. So it's not something that happens just on one weird star, so we can forget about. They are common, and also what I find very interesting is that sometimes they share similar time scales. So we do see time scales that repeat from one outburst of one star to the other, which tells us something about the physics of the process that we still don't know is happening. So we said it's common, but every time that we could have a look for the stars responsible for this behavior, we were used to find big stars, which was good and bad for the field because the prompt reaction was, well, you know what, maybe this is common among massive stars, but doesn't go all the way to the low mass stellar progenitors of normal supernovae. And I'll try to convince you that the answer to this question is a no, is a big no. Is that only happening to very massive stars? No. And I'm going to provide you evidence for that. All right. So if I were to draw a panel of where possible discovery areas are in the field right now, I would say that definitely the pre-supernova outbursts, so whatever happens in the years before the actual supernova explosion, is a very active area of investigation right now. And LSSC is going to provide a gold mine there. So we will be able literally to sample all these time scales of outbursts. This is definitely one of the discovery frontiers I'm excited about for the near future. So the other tool that we use to investigate the recent past of the stars that are exploding is called flash spectroscopy. So here, the physics behind the concept is very simple. We have a supernova shock, and supernova light illuminates material here. This material gets ionized and then recombines. And what we do is we try to get on target as fast as we can to sample in real time the recombination. So why is this a beautiful tool? Because it tells you the chemical compositions of the very outer layers of the star just before stellar death, which is a proxy to understand at which point in stellar evolution that star exploded. And you might wonder, why do we need to know that? Because a number of times we see stars that explode when our theories are telling us they should not yet. That's why it's so interesting. And then there is a third tool, which is probably my favorite, which is shock interaction. It's something similar to what I introduced already this morning, but let me go through a little bit into detail. So here is the main idea. So these two tools, flash spectroscopy and direct observations, tell us what the star has been doing in the few years before dying. So how do we go back to the 1,000 years that I've been telling you? Here's how we do it. So the basic concept here is that our star, before exploding, has been putting in the environment a lot of material. That and then what happens is that when the star explodes, the shock is going to sample this material. It's going to accelerate particles, and these particles, these electrons, are going to radiate through synchrotron, Bremsstrahlung, inverse Compton. So they're going to radiate in the X-rays and radio. So the beauty of this method is that if you have a medium that is more complex, in principle, you should be able to reconstruct this profile just by sampling the X-rays and radio. But there is something that is even more beautiful, which is this thing. The typical shock velocity of a supernova is much, much larger than the typical ejection velocity of material before, which means that the shock catches up very quickly with material that was ejected before stellar death. So at every time t of my follow-up observation, I'm sampling the life of this star that was a fraction v shock over v ejection, which can be 30 times, 500 times, 1,000 times t. So effectively, the shock works just like a time machine. So it can tell you what the star has been doing before. So this is the way we use to investigate what the star has been doing in the last centuries, in the last 1,000 years, just before death. That's how it works. So while doing this exercise for a bunch of supernovae, type of supernovae, and here I put an arrow just to guide you through it. The level of stripping of the star goes in this direction. So here are stars that have some hydrogen around, and those are stars that were avoided of hydrogen by the time of their collapse. So what we are finding right now is a sort of a sequence where you have that stars that explode as a bare core, they tend to have fast ejecta and also low densities. And this depends on the mass loss from the massive star. While stars that at the time of collapse were able to retain some envelope around, they tend to explode in high density environments, which is telling you that these stars were most likely suffering from heavier mass loss before stellar death. So this is the picture that is emerging right now. So this is one of the first hints for a connection between the stellar progenitor structure before death and what the star was doing before collapsing. Of course, while doing this exercise, we encountered things which are a little bit less well-behaved than the typical wind material that we were expecting. And this is one of those, the supernova 14C that sort of sent us back to the drawing board. So let me walk you through this transient. And also, with this supernova, we were able to have a hard X-ray image of an extragalactic supernova for the first time. So that's kind of cool. Okay, so for X-ray astronomers that are here, I think they can understand my happiness, because it means that for once we can sample the entire spectrum. So I can measure temperature. So with Chandra and Nuster, we have temperature from spectra, which means effectively velocity of the shock, which means I can reconstruct the dynamics of the shock. So I think the X-ray astronomers can understand my happiness in being able to constrain parameters just like every other part of the spectrum for the first time. Okay, so why the supernova 14C stands out? So why this supernova sent us back to the drawing board? Let me give you a 5 minutes explanation. So when I was in grad school, they told me that supernovae are classified either as type 1 or type 2. No hydrogen? Yes, hydrogen. Yes, hydrogen. That's it. And here is an example of a supernova that totally disrupted this type of classification scheme and really demonstrated that you can be born as a type 1 and then transition into the type 2. It was the first time we could see it in real time. And for a number of other objects, we had suspicion that this can happen, but this is the first time that we could see it as it was happening. So here it is. Who was 14C? So forget about all the details here. The key message is that it was a very, very unremarkable supernova in the nearby universe, which is very important as a message. So very typical. Nothing at the early times was peculiar. However, we have been persistent, and we kept staring at our location in the sky, and we saw that a supernova that started with no hydrogen, this is hydrogen from the host, so don't get confused there, started building up this fatty profile of hydrogen. So we have a hydrogen strip supernova that is building out hydrogen with time. Then we decided to have a look in the radio. And what you have here is the entire world of supernovae, hydrogen strip supernovae in the radio. And if you plot 14C here is how it looks like. And I can tell you that here there is another data point that I didn't have, I forgot to add. So it's still rising. So you have a rising radio light curve 1,000 days after the explosion. That's to play the same game in the X-rays. And if you thought that this was kind of sad, if you think there are 40,000 optical supernova, this is the entire world of radio. And look at the X-rays though. This is miserable compared. So if you put there 14C, this is how it looks like. So it goes up with time, and it's still there at peak. So we have, putting everything together, we have a transient, a supernova, that went from type 1 to type 2, so produced hydrogen, and at the same time it rebrightened in the X-rays and radio. So I think that by now you're understanding what's going on here. So we had a supernova that happened to explode in an environment that close by was normal. However, for reasons that we're trying to understand, this shock encountered a wall of hydrogen that was there, and thanks to the fact that we could resolve the dynamics of the explosion, we can tell you where this hydrogen was. So it was close by. That's the message, which means that the progenitor of this supernova probably experienced this ejection of hydrogen very, very close in time to the time of stellar death. Okay? So why? The big question is, okay, now I can describe the situation. We have hydrogen very close by, so why is there? So we thought about two possibilities, and the first one is that we know that recent simulations are showing that there are instabilities in nuclear burning sequence that we were not really appreciating until now. So it's possible that some of these instabilities actually actually happened during the very last phases of evolution, and so maybe this is a way that we can find to put at the base of the envelope of the hydrogen envelope some energy to explode it. So that's one possibility. The second possibility is that we are not alone. There is a companion star, and the interaction with the companion star is the one providing this little extra energy to explode our envelope. And you do understand that these two scenarios are impossible to distinguish based on one single object. I can't tell you which of these is right. However, you also appreciate that if nuclear burning instabilities are responsible, well, that should always happen at the end, right? That's a mechanism that knows that the end is coming. If instead binary evolution is the one responsible for it, well, in that case, I would expect the companion not to really know exactly that I'm about to explode. So if the binary interaction is responsible, I would expect this kind of ejections to be almost uniformly spaced out in time before death. So this means that if we can do a sample study of all these explosions, and we can pin down when this ejection happens, we will be in the position to say which of the two mechanisms is right. Once we realized that, we decided, okay, let's see what we have. So we went back and looked through the entire VLA archive, radio archive, looking for things that would show this kind of late time, right? They told me not to use mine, so that's why I keep it. So I'm trying to be good. Okay, so showing this late time rise in the radio, and we could find 4 of them, which means, doing statistics, that at least 10% of these stars that produce normal supernovae, they also do this kind of eruptions. However, I also wanted to quantify my ignorance. So, and the ignorance here are these shaded bars here. So I put down here as a function of time since the explosion, what's my ignorance about the question, is the supernova shock interacting with this wall of hydrogen or not? And you can see that these bars are huge. So what we're trying to do right now is to actually design an experiment with the VLA and try to really pin down these fractions following up until very late times nearby supernovae in the universe. The dream would be to then connect these time scales to the nuclear burning sequence and see if the time of the ejection correlates with some specific time in the nuclear burning sequence of the star, which would allow us to make a connection between nuclear burning instabilities and these ejections. So here is a slide just to put together all I told you about our ways to try to investigate the past of the stars. So with tools that allows us to investigate the few years before, and supernova shock interaction as the only tool right now that allows us to go back in time all the way to 1,000 years. Okay, so enough about this part. Let me tell you what we have been doing or trying to do to get closer to that other part. So what supernova, what explosion produces what compact object? This is an extremely intriguing question for me. And of course, we know that they do it. And we know that because explosions in our backyard, well, we can see the neutron star there, so we know that they do it. The question is, can we extend this knowledge to faraway explosions? So the problem is the following, that the compact object, even if it is born at the very early times, has a lot of ejecta around. So at the beginning, all the photons from this compact object, if it's still alive, will have to fight through this amount of ejecta. However, with time, the ejecta is expanding, so effectively diluting, which at some point means that maybe photons from this compact object has some hope to get out. And here I put a couple of plots that I really, really like about studies of late-time spectroscopy of kind of oldish supernovae. And what these studies are finding is that it's possible that these high ionization emission lines are actually due to the fact that we still have a light bulb that is still active in the middle of the ejecta. So if I were to put another of the discovery areas into this plot, I would say that very late time spectroscopy of explosions, maybe with the ELTs, like the extremely large telescopes, is going to tell us a lot about what was born inside the supernovae. So that's another area where I think is going to be extremely interesting in the near future. However, I think that you already appreciate the fact that if, by any chance, I have an explosion that has very little ejecta, well, then I don't have to wait for a long time, and maybe I get transparent soon, so I get the chance to see through it very, very early. Or maybe if I have an ejecta that is asymmetric, again, this gives me the possibility, this gives the photons from the compact object some possibility to go through it at earlier times. So both of these two things are actually very much related to the third discovery area that I want to discuss with you, and potentially the ones that I'm mostly excited about, which is this area in orange that has the very fast evolving transients. So transients that go to peak in a few days. As I told you, this is an area that we can now sample just because the cadence of our surveys are way better than before. So let's have a closer look to this transient. And here I borrowed a plot from Maria Drought paper. And I'm sure you all remember Maria here. So Maria did some pioneer work in this field of fast rising objects. So first of all, how do we call them? So the literature is so young that we still don't agree. So sometimes you would find them as called like fast and blue optical transients, FBOTs for the friends. And some other times they're called FELTs, fast evolving luminous transients. But the meaning is that they're fast and they evolve on very short time scales. So let's plot them on a luminosity versus time scale plot. And let's compare them to the other usual explosions we have been used to until now. And our FBOTs are the stars, and the collection of stars here is from Maria's work, and I put there some more that have been found later on. So first of all, here is where type 1As are. You can recognize the strip that is so close to the heart of people doing cosmology. That's the reason why we can do cosmology in the first place. And superluminous supernovae that I told you about this morning, they are here, up here. And the normal supernovae, they are all around here in gray. So the first thing I want you to appreciate is that this transient with very short time scales, they span a huge luminosity range, which might suggest some sort of diversity within the class, right? The other thing is that this transient, until now, has been reported to happen in the star-forming galaxies, so usually star-forming galaxies. So what can we learn about this transient? So first of all, let's start with their common feature, which is this very short time scale. So, and let's think about the case where our energy source that is powering my explosion is sitting deep down in the center. In this case, if the source of energy is here in the center and you have to get to peak in 2 days, that becomes a statement about the amount of ejecta that you have around. And here I put a simple, very simple calculation. With a peak time of a few days, you need an ejecta mass that is point something solar masses, tiny. Normal supernovae, they have from 2 to several solar masses. So this small ejecta mass automatically rules out the normal way supernovae are powered through nickel 56. It's very similar to the argument that I used this morning. So it's simply because in order to power the peak, you would need something like 6 solar masses of nickel, but yet you can afford a point something because of the time scale. So right away we know that if these transients are powered by a central source, this is not the usual source we're used to. There is another way you can explain this transient is, okay, forget about the central source, which might be there, but is not responsible for the peak luminosity. I'm going to use interaction as a source of energy, so something outside. So in that case, the very short time scale of the peak tells you right away something about where this breakout radius is, so where you produce radiation. So in this shock breakout scenario, it has 2 key predictions, which is that, first of all, you would expect to cool with time, right? I have a shock, it goes through stuff, and then the shock is ahead and the stuff will cool down. There is no heating anymore. The other thing is that you do not expect to see fast variability time scale because you're limited by basically the geometrical effect of the radius that you're sampling. So those are the 2 scenarios. Until now, both of these scenarios were actually able to coexist in the literature for fast evolving transients, mostly because most of these transients, all of these transients apart from a couple, are found at very large distances, so we could not do effectively a good multi-wavelength study. That's the main reason. So things changed, and here is where I say, well, in Latin we speak about lions. I think English people say dragons, but here I think we should be speaking about cows. And I think this is one of my major achievements, is that I had a title like Holy Cow a few days ago. Yeah, I think it's the major achievement that I should put there. So is it why we speak about a cow? Because this transient, astronomical transient 2018 COW, just happened to sound very much like a cow. So it became soon the cow for everybody. Yeah. That's very funny. So what is special about the cow apart from the great name? So here is a picture of where the cow was born. And let me zoom in. This is the cow at this thing. So off-center, first thing is off-center. And the distance is 60 megaparsecs, which for us and for this specific type of transient means very close by. So good, very good opportunity to do follow-up outside the optical. So once we realized that, we started a massive multi-wavelength campaign with all of these instruments listed there. And this can only happen if you have a great team behind, where each of these people really helped out a lot. So this is my way to say thank you, and you are gonna recognize a lot of names here. So why we got so excited? So what made us so excited about the cow? So first of all, let me place the cow in this R band versus time plot. And if you were just to look in the R band, you would say, yes, it goes up and down very quickly, much way quicker than any other supernova we know about. But you say, yeah, it's kind of luminous, but yeah, fine. However, the cow is extremely hot. So the bolometric correction to the R band is huge. And if you do that with a temperature of 30,000 Kelvin, it brings the cow all the way up, even higher than some superluminous supernovae. So it's extremely luminous transient on a very short time scale. So let's establish some basic properties of the cow. I'm going to do this kind of game in optical, then X-rays, then radio, and then we're going to go back to the X-rays. So let's establish some key properties. So you're looking at spectra here, series of spectra during the first 90 days. And the first thing to take away from the spectra is that the spectra were mostly featureless. And it's almost impossible to tell anything from this first spectra, apart from the fact that, yes, you need high velocity material. And then it develops. And then he develops hydrogen and helium, though, at velocities which are way smaller. This is extremely important because right away it rules out models like neutron star mergers, which would have been one of our first guesses. So while this thing is doing that, the luminosity, the bolometric luminosity in the optical goes down after having get to the top in 2 days. It goes down with like a beautiful power law, almost one of the best power laws I've seen. And while this is happening, let's have a look at the temperature evolution. So temperature here is the black ones, and I want you to draw home one concept here is that it stops cooling. It stops cooling. As supernovae, they do cool. They keep cooling. And if you remember the shock breakout model, it would be expected to cool down. But this is not cooling. Let's have a look at this transiency in the X-rays. And for now, just concentrate on the soft X-rays, 0.3 to 10 keV, the black points here. And you can clearly see that it's a highly variable signal. Not only is it highly variable, but it also abruptly shut off here. Again, if you think about what I just told you about the shock breakout thing, you would not expect high variability there. Okay? So it seems that the shock breakout is running into a couple of issues already. So, and this is luminous though in the X-rays, so luminous that at the beginning, some of us got a little bit fooled out and thought it was a gamma ray burst. So it's as luminous as a gamma ray burst at early times. So let's have a look at this thing on the other side of the spectrum in the radio. And here, with some little complication, that's probably the place where the transient is well behaved. In the sense that for people doing supernovae, they recognize a typical synchrotron spectrum cascading down with time. And if you, and actually the high frequency range was part of a focus study by the Caltech group by Anaho. And for people that do supernovae transients, well, this looks like a pretty well-behaved synchrotron spectrum with a synchronous self-absorbed part here, and then an optical lithium part down there. So you can apply the usual scaling that you do for synchrotron, and from the flux, peak flux, and the peak frequency, you can infer properties like the radius of the blast wave, so the velocity, the kinetic energy, and so on. So let's do it. So what do we find? So if we play that game and place 18 cow on a plot, which is the plot of the radio observables, radio luminosity, peak frequency times when you peak. Well, 18 cow lies here, and let me tell you what this means in this plot. So first of all, it lies basically, roughly, on this line, thick black line, which is a line of a shock that moves at 0.1 C. So roughly, the first message is that, okay, we are dealing with a shock that is not ultra-relativistic. It's 0.1 C. It's not a gamma ray burst-like thing. The other thing is that these other lines instead tell you something about the density of the environment where this blast wave is propagating. And what you get out of this plot is that it is in between these lines, and we quantify things in A star. Think about A star as the typical mass loss rate from a Wolf-Rayet. So the message here is that the environment of this blast wave is dense. So it's not low density, it's a dense environment. And if you do numbers, you would be able to also derive the typical energy of this shock wave, and the equipartition energy is around 10 to the 48 erg. So it's kind of pretty healthy as a shock, but not GRB-like healthy. if you put, consistent with our inferences of the previous slide, if you put the cow in the radio space, you would see that the cow is way more similar to a normal supernova in black than gamma ray bursts, which are here. So it seems that the radio is telling you that you're dealing with, we have a shock that is propagating in the environment, typical velocity 0.1 c. All in all, not that dissimilar from a supernova. So let's put everything together. I know this slide is dense. And the way I look at things is that broadband SEDs are truths. They tell you what really is going on. And what you have here is a sequence of SEDs with time. And you have in blue the radio, which is, as I just told you, is sort of okay with an external shock interaction with the medium. Then we have the X-rays here in orange. And from the fast timescale variability, we think, and the fact that the X-rays do not speak to the radio, they are way in excess to our model, we think that the X-rays are coming from an inner source, not from the shock interaction. And then we have the optical that is not cooling. So our idea is that the optical is getting reheated by the central source of energy that is shining in the X-rays. That's the main idea. And our way to visualize all of this is this beautiful cartoon put together by Nathan Roth, where we have this source, which we call X-ray source. We do not know exactly what it is. It can be a black hole there, neutron star. It can be a shock there producing X-rays. So all we need is a light bulb of hard X-ray radiation. And that is shining through very asymmetrically distributed material. Why I need to break the asymmetry is going to become clearer in the next slide, but let me just tell you one reason more. Is because if you look at the profile of these emission lines, this is skewed to the red. It's red shifted, and that's a clear indication that you need to break the spherical symmetry and to have more emission, see more emission coming from this side, because we are there, instead of things that are coming from this other side. Okay, so this is our model. And I told you that you're going to appreciate why I need to break the spherical symmetry in a second. And here is, I'm getting to the part that was the most exciting of all, I think, during this campaign, which is very much connected to this thing. So at the end of the day, this picture of a source of X-rays embedded into some material that is asymmetrically distributed is not that far away from what we have in mind for X-ray binaries or even agents, right? And these are sources that they are known to produce, you are the experts here, I'm saying it, but people here are the real experts of this Compton hump spectra with, this is the Compton hump, and with a beautiful iron K alpha line. So that's a very typical feature. And so keep in mind that plot. And here is how the cow looks like at day 7. So I'm not used to stare at this plot, and that for me was a complete surprise. So let me tell you in 1 second the story here. So we were monitoring things in the soft X-rays, and I thought, well, I really want to understand if these X-rays are thermal or non-thermal. So I was either looking for a continuation of my power law for the non-thermal process, or a more steeper or a steeper decline of the power law. That was, and so I wrote a DDT to Fiona with that scientific case, and here you go. I got the third possibility, a rising spectrum instead. So my first reaction was, let's go back and check the data reduction. And then we spoke with the integral team, and yeah, we saw that both instruments were finding this excess. And then we got convinced that this other excess was also real. So if you go back again, this is what we see in this Compton spectra, and here we go. So what we think is going on here is that we do see part of the X-ray emission from the source coming directly at us. This is our source. But that we have some material around that is reprocessing, doing the Comptonization. And this is what producing this beautiful feature. But there is something more. So not only we find the Compton, this what I call Compton hump, the hump here, but if you have a look, this is the evolution with time of the high energy spectrum. You will see that here we have it. Maybe there is a little hint here, and then it goes away. So this feature is transient. It goes away. So what we think it is, and we ran indirect worm actually ran some simulations to verify, is that we have our compact object that is, or something that is producing X-rays. We have a medium that is reprocessing these X-rays, but this medium is expanding. So with time, is losing its capability to reprocess the radiation. So this causes the hump feature and the connected excess here to go down and disappear in time. So a typical way to produce a Compton hump that we think about is that we have absorption helping us out here, absorbing X-rays, and then on the other hand we do Compton scattering. Okay, now okay, here we go. So we were so excited that we even attempted the modeling with the typical models that some of you are way more familiar than I am. And here we got great help from our collaborators. And here is the result of this modeling with a Comptonized disk reflection model that is very much used in X-ray binaries. So it seems that, yes, we can reproduce very well our observations, and it seems amazing to me that we can also reproduce the little excess, which we think is literally related to iron emission there. There is a little thing that is, I find extremely interesting, is that, okay, let's assume that this is accretion. Let's assume that the same thing that happens in X-ray binaries and HGNs is happening here. Well, here we have a luminosity of 10 to the 43 erg per second. So if we formed a black hole, stellar black hole mass, a black hole of stellar mass, of a few stellar mass, well, that needs to be more than a little super Eddington. So that's a little problem. Okay, so if you don't remember anything out of this talk, just remember this: that there is a cow in the sky. It's a spherical intention engine. That's the punchline of the paper. So, so this concludes my tour through this, what I believe are going to be very exciting discovery areas in the future. And in particular, I'm very excited about the fact that, yes, we can do a good job now, even for the fast-evolving transients, and we can see what they do outside the optical. And I hope I convinced you that even if for most transients they put most of their energy in the optical, I hope I convinced you that there is a lot of value to go outside the optical. And here is a slide that I use in class to convince the students that, yes, it's good to open your eyes to the entire spectrum, because there is tons of information because different processes dominate at different wavelengths. And yeah, this is the end, and it's literally where we start, is the end of stellar evolution. And with this, I want to thank you for your attention.
Thank you very much, Raffaella, for a great talk. Questions?
Beautiful work. I just want to ask you about the scales involved. So you said 10 to the 43 ergs. You know, at what period in the evolution would it have been that, or is that a total? And what about, if this is a disk, what would be the spatial scale of the disk?
That's a great question. So the first one is easy. I can show you the data. So that was there at 7 days is when the Compton hump feature was there. And about the scales, we went back and forth, and we tried to estimate that. We do not have actually an answer. So we decided, okay, let's let it there as a speculation, and as a further work, we will try to pin down the actual parameters. Yeah, but you would need to produce this feature here. You need to go far away that your ionization parameter gets low enough to produce this iron. So it needs to be hundreds of RG. Yeah.
This is really beautiful stuff. This is the first evidence for the formation of a stellar mass black hole. It really is, yes.
Yeah.
There's never been anything that resembles a supernova before. That obviously we don't see it in any of the known black hole X-ray binaries, which are the only ones we could look at previously. But the luminosity really is a problem. That's over 100 L Eddington for any stellar mass black hole we've ever seen. So what about beaming?
Yes,
That's the usual way out.
Beaming is always the way to do this stuff. Yeah, I agree. Maybe there is beaming. The other thing that we thought about is that for the ultra-luminous X-ray sources, they get to 100 times, 1,000 times Eddington, and so we were hoping that people like Ramesh would come out with a way to do the same for this kind of system. But yeah, I don't have more than this way.
I was going to ask you the same question that Ramesh asked this morning. That these late, well, not so late time signatures could be due to not magnetars, but black hole formation, and this clearly must be the case here.
Yeah, I would be. So the reason why I'm so excited about this transients is because I think they might provide us with this opportunity to see what these compact objects do right away when they are formed. That's why I think it's potentially very exciting. Yeah.
I have a question about 2014C.
Yes.
We took data for it, for Danny, by the way, in November 2016. So it's almost 3 years past the explosion.
Yeah.
And it was shining in the K-band, which was like quickly interpreted as possible interaction with the warming up of the dust around it. So how does it go in line with this idea of hydrogen shock? And it was like almost 3 years later.
Well, I think it does. It really goes along because you can think about the shock to be the one heating up the dust. Yeah, totally type.
So it's further away.
Yeah. That would be my guess. Yeah.
So after we talked in my office just about an hour ago, right? You came here to connect your computer.
Yeah.
I went and looked at some of our old models.
Oh, man.
Since Josh asked, I can tell you, we have a paper on ULXs, and it was not intermediate mass black hole. We just looked at 10 solar mass black holes, but very super Eddington accretion. And we don't have 10 to the 43, but we got 10 to the 41 Earths per second. And my guess is if we push the knob even some more.
And the corona, the quantization in the corona might give you an extra 10, right? To boost it up a little bit.
Well, it was 10 to the 41 in the bag.
Okay.
Yeah.
Okay.
It was all in X-rays, yeah.
Okay.
So we should talk. And actually you met Brandon, right?
Yes.
So he can run the simulation with even a more accretion rate, and maybe we can do something.
Fantastic. That's fantastic.
And then we can believe that it's a black hole. John, at the moment I'm not yet convinced that this is a black hole. Yeah.
See.
Yeah.
The mystery deepens.
Yeah.
Other questions? Okay, if not, let's thank Raffaella
Thank you
again.
very much.